Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the linear transformation of a continuous random variable. Specifically, we're looking at if I change x to ax plus b, what will happen to the expected value and variance. Here, large letters mean random variable and the small letters are just constants. So to illustrate what happens, I'm actually going to use this data here. I've just made up 4 scores from our weekly Canvas quiz. Now I know that this data is actually discrete, but the same process will work for a continuous random variable, and this will illustrate it a lot more easily. So let's say 4 people took the weekly Canvas quiz, and these are their scores 5, 7, 8, and 8. So here I'm just saying, 5 occurs with probability a quarter, 7 with probability a quarter, and so on. So to find the mean or expected value of these scores, I simply add them all up and divide by how many there are. So the mean of these 4 numbers is 7. That's the same answer I would get if I went 5 times a quarter plus 7 times a quarter plus 8 times a quarter plus 8 times a quarter. Okay, means just 7. Turns out that the variance of these 4 numbers, 5, 7, 8, and 8, is just 1.5, and so the standard deviation is just the square root of the variance, which is about 1.2247. So don't worry how I calculated the variance and standard deviation. We did that last semester, but I'm just using it here for illustrative purposes. Okay, so nothing groundbreaking at the moment. Now, what would happen if I added 1 to everybody's scores? Let's say I accidentally put in the wrong answer in Canvas. I marked people wrong when they're actually right. So if I add 1 to each score, of course, the scores become 6, 8, 9, and 9. So it turns out that the expected value, the new mean, if I add up all these scores and divide by 4, I get 8. So the mean actually has increased by 1 if I add 1 to each score. It turns out, however, the variance is still 1.5. So adding a number to each of the scores does not change the variance, and consequently that means it doesn't change the standard deviation. They stay the same. So what about if, because I absolutely love this class, I decide to double everyone's scores? Well then, the new scores would be 10, 14, 16, and 16. If I find the mean of these 4 scores, turns out I get 14. So when I've doubled each score, I've actually doubled the mean. So what would happen to the variance of these scores? So don't worry how I calculate it, but I end up getting a variance of 6. You see, if I double each score, I multiply the variance not by 2, but by 2 squared. And so what that means is the standard deviation will now be the square root of 6, square root of the variance, which is about 2.4495. What's happened is the standard deviation, like the mean, has been multiplied by 2. So what's actually going on here? So what I've found is if I add a number b to each of the scores, that's what this is saying here, then all that does is increase the mean by whatever I've added. So that's how I get this formula here. If I add b, a number to each score, it doesn't change the variance and it doesn't change the standard deviation. So if I multiply each score by a number a, I also multiply the expected value by that much. So if I triple each score, I triple the expected value. But it doesn't work the same for variance. If I multiply each score by a, I need to multiply the variance by a squared. So if I triple each score, the variance would be 9 times larger. And if I multiply each score by a, the standard deviation also multiplies by a. So these are the 3 formula you need to know. This is what happens when you add something to each score and multiply each score by a constant. So let's look at calculating these on the next slide. So let's say x follows a uniform distribution and x is between 5 and 12. We're going to calculate the expected value of 3x minus 2 and the standard deviation of 3x minus 2. So to calculate this, we're first going to calculate the expected value of x and the variance of x. Then we're going to use those rules on the previous slide to calculate each of these. So remember, if x follows a uniform distribution with lower limit a, upper limit b, remember the expected value is just adding up the two numbers and dividing by 2, and the variance is b minus a squared, all divided by 12. So, if x follows a uniform distribution, x from 5 to 12, a is 5, b is 12, that means that the expected value of x is 5 plus 12 over 2. It means that the variance of x is 12 minus 5, which is 7 squared, 49, divided by 12. So if we calculate E of x, expected value of x, we can calculate this really simply. The expected value of 3x minus 2 is just going to be 3 times the expected value of x minus 2, which equals 23.5. So let's calculate the variance of 3x minus 2. So the variance of 3x minus 2, so remember, the minus 2 part, subtracting 2 from each score, doesn't change the variance, but if you multiply each score by 3, you multiply the variance by 9. So the variance would simply be 9 times 49 over 12. So the variance would be 36.75, and so the standard deviation of 3x minus 2 is just the square root of the variance, which is about 6.06. So if you're asked to calculate expected value, variance, or standard deviation of ax plus b, first calculate E of x and variance of x in the normal way, and then use the rules on the previous slide. So let's do one example that's a little harder. So we're going to calculate the expected value and variance of 5x plus 1 on 2, where x is a continuous random variable with this PDF between 1 and 4. So as I said previously, what we're going to first do is calculate E of x and also variance of x, and then use the rules for expectation and variance on the first slide. So this one's a bit more tricky because we have to go through the integration process to find expected value and variance. So the expected value of a random variable, you multiply x by its PDF and you integrate from the lower to upper possibilities for x. So of course, x times x squared is just x cubed. We're integrating x cubed over 21, so we're going to use the rule increase the power by 1, divide by the new power, evaluate between 1 and 4, and we get 85 over 28. So that's the expected value of x. So the expected value of 5x plus 1 on 2, we're just going to make this a little easier on ourselves. That is the same as 5 over 2 times x plus 1 over 2. So using the rules for expectation, we just multiply 5 over 2 by our expected value and then add a half. So putting that into our calculator, we get about 8.09, and we're done with the expected value. So now we're just going to calculate the variance of x. Again, it's a little trickier because we don't have a nice formula to use. We're going to have to integrate of x minus the expected value squared multiplied by the probability density function, and of course don't forget to write dx. So we firstly expand the brackets to get this, and then we times each term in the brackets by this PDF. And now we're ready to integrate. We're just going to increase the power by 1, divide by the new power for each of these 3 terms. So then, of course, we just substitute 1 and 4 into this expression. I get this, and my answer for the variance is about 0.527. So these calculations were long and messy, yes, But now that I've calculated variance of x, it's really easy to calculate this variance of 5x plus 1 on 2. So again, I'm going to write it like this to make it easy for myself. Now it's in ax plus b form. Remember, this plus a half doesn't affect or change the variance at all. And this number in front of x, we have to square it and multiply by the variance of x. So this variance will be the original variance, not times 5 over 2, but times 5 over 2 squared. So, of course, when I'm putting this on my calculator, I don't want to round it to 0.527. I'm just going to press the answer button, so I get more decimal places, times 5 over 2 squared, and we end up with an answer about 3.3, and we're done. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.